seems to represent an interesting approach for several clinical applications. And on the other hand, such a laser are applicable for interferometers, for laser printing and digital photo finishing and data recording in laser microscopy and for spectroscopic measurements. In this paper, we present the results of the influence of blue lasers parameters on cell pulsation properties, and we studied the influence of thickness of the saturation absorber, the length of the laser, as well as lifetime of carriers on the cell pulsation region. Why cell pulsating lasers? Cell pulsating lasers offer possibility to reduce drastically the noise, which is very important to reduce noise in different applications. And this is a structure of investigated, and it consists of active region of active region, indium gallium, and this is 3 quantum wells of the indium gallium n type, and the saturable absorber. Such a laser was built in Japan at Sharp company, and our colleagues from Japan provided us with experimental results. And the thickness of the active region and saturable absorber is 80 nanometer, and the wavelength is around 405 nanometer. The length of the device is 650 micrometer. I have to mention here that we also investigated the lasers with 400 micrometer lengths and 550 micrometer laser. But here in this paper we presented only the laser with active layer of 650 micrometer. And you see here that substrate is gallium N, and it comes from Poland. The substrate of this device is gallium N, and it comes from Poland because the best substrate which is built up to now is done in Poland, where the company provide such a substrate. And the theoretical model is used to describe the laser dynamics is based on this model, where S is a photon number in the full device, S, and N is the number of charge carriers injected into the region. This means for each region of this structure we have one equation. And I have to mention here that we included the leakage current, and the leakage current is around 35% of current which is applied. This means 38 or 35% of current is just used for heating, but not for emitting of light. It's huge. But nevertheless, the structure which is built up to now gives this leakage current. Maybe next generation of such devices will be much better. On the other hand, when this memory stick appears, then the interest to such a laser decreases due to the fact that such lasers were used for blue disk to write the information, and when memory stick appears, the interest decreases. But now, since such a laser are used in medicine, there is an interest in such devices. The second equation is for the number of charge carriers injected into a region. As I said, for each region we wrote an equation, and we have these coefficients. The amplification saturation coefficient is given by this expression, and you observe that in this expression there are a lot of parameters, and we used many of these parameters we obtain them from the real device in order to compare theory with the experiment. The threshold level of amplification is given by this expression, where we have front facet reflectivity, which is 25%, and back facet reflectivity, which is 95%, and the losses also is too high due to the fact that in such devices we have damages or defects, and this is the loss coefficient which was obtained from real device. And here we start with the dependence of output power on injected current, which is from 0 to 200 milliampere, and we observe a threshold around 78 milliampere, and then there is a CW operation, and after that the cell pulsation appears. And this is on the left side is what is obtained from experiment. In the right side it's what we obtain from numerical simulation. Such a behavior is obtained in this region, and you can see that there is a good agreement between experiment and theory. For bifurcation, here we have Hopf bifurcation. Hopf bifurcation is a bifurcation which separates the stable emission. Stable emission is just a stable node, stable focus, and non-stable emission here, which is cell pulsation. Let's look a bifurcation diagram, and the white region there is no any lasing, and the yellow region is CW operation, yes, and the cell pulsation region is very wide, and it can be observed for a wide region. The red line, this is the threshold current, and you observe that there is a small region where just after the threshold the cell pulsation appear. And this one also was proved just for one line, for example, in the experiment. Now let's look how different parameters influence the region of cell pulsation. The region of cell pulsation is shown in this figure. For example, here is different absorber thickness, and when we decrease the absorber thickness, then the region of cell pulsation decreases, but on the other hand, the threshold, which is here, also decreases. Yeah, for higher thickness of Saturov absorber, it is clear we have a wide, but we need to apply higher currents always because the losses are increased. Let's look here. We have carrier lifetime in the Saturov absorber. This is a very important parameter, and since we have just a single quantum well in Saturov absorber, the carrier lifetime was less than 1 nanosecond, and this one was not accepted by community because always they said, okay, we have more than 2 here is not nanometer but is nanoseconds, 2 nanosecond, and this was proven in experiments, but also we show that when you consider just a single quantum well, then you can get very low threshold, very low carrier lifetime. And in this case, you see for different thickness of saturobro-absorbo, the region of pulsation is different. Here we have for small, here we have for large. And also the differential gain doesn't affect so much the region of pulsation. Within this region, if you keep the temperature constant, you can stay, for example, as long as the laser will operate within this region. This region is characterized by low noise. For example, if you change the current from this position to this position, you will observe completely different level of noise. Now, let's look for region of pulsation for different coefficient of back facet reflectivity. When you consider 0.2, in this case there is no resonator and there is no and also no lasing of laser. When you increase back facet reflectivity, then this you can call this as a laser, and in this case we have a wide region of pulsation. And we confirm this one because at Kanazawa University we had some lasers with a very low reflectivity, and this, as Professor Yamada called, damaged lasers. But nevertheless, they confirm that, okay, for such a laser which are not good, we also can get a region of pulsation. And we look for frequency of pulsation. And we got the line with the same frequency, for example, 0.55 gigahertz, 0.75, 0.9, and of course, someone will tell, oh, this is not so high, we need at least pulsation more than 1 gigahertz. And I will tell you that we reach such a pulsation. For example, we plotted here variation of frequency of pulsation in the plane of length of a resonator and different parameters, and you can find that, okay, this region is characterized by up to 2 gigahertz, and this region is characterized by 3 gigahertz. And the current is just usual current of 100 milliampere, not so high current. Finally, my conclusion in this work, the domain of cell pulsation were obtained in the plane of different parameters, and it was concluded that the thickness of the saturobro-absorbo, carrier lifetime in the saturobro-absorbo play an essential role in the dynamic of laser. Also, we show that cell pulsation with frequency up to 3 gigahertz range were detected by numerical calculation, but also in the experiment. Thank you for your attention.
Thank you for the presentation. Now the session is open for questions. Leonid? Well, why pulsating is important?
It is important due to the fact that the level of noise in the pulsation is reduced many times. Yeah, when you have CW operation, yes, you will have such oscillation, you will come to a focus. But this focus is not stable. You will see in the spectral noise, very wide noise. When it's pulsating, something like this, then the noise is present, but the noise is very small and it goes up to this one. And this one is it's much better for some applications.
Yes, yes, okay. And what what kind of application I expect?
Okay, let's look. You write a CD, yes, because even we have such a memory stick, we still need to write the information at big companies to some CD. Up to now, it was CD 700 megabytes, DVD 4.7 gigabyte, yes. And if you have with blue, you can increase, for example, up to 50 or something like this. And then you can put and to write the information many times to such a devices.
Yes.
And also in medicine, in medicine, under communication under sea, also they use such a lasers.
Yes, thank you. And the resonator is Fabry-Pérot type?
Yes, it's Fabry-Pérot
How
type.
it is made? By natural surfaces?
Okay, this is a little bit complicated for me. Only what I know, it's structure. I assisted just how they grow this structure, but only I know each level, each layer, the properties, and so substrate, I know where it comes from, and each layer, the thickness and the properties.
Thank you. More questions?
Yeah.
Leonid?
Very nice presentation,
Thank
but
you.
I have a question. Why we have so big dependencies laser emission wavelength on current from this power?
I mean, you mean the region of cell pulsation?
Да.
Yes, this is.
Very big dependency.
Yeah, it
Three
is.
times.
It is such a dependence on the injected current, but the Japanese people said to me, okay, we have such a devices, we need pulsation. You have to deliver because they cannot grow every time and to look for new devices, new properties. And the idea was, okay, I got in some region pulsation, yeah, and after that they looked, they found it, and after that they told that, okay, we will fix it the current, we will keep the current at fixed value 150, and there is no any change of temperature, then the pulsation will stay on this current. And that's all.
Thank you again for your presentation. And the next talk will be given by Sergiu Cojocaru from the Magurele, Romania, with the topic Parametric Anomaly of the Phonon Spectrum of a Thin Freestanding Membrane.
Thank you.
Maybe. Okay, I will have to use the keyboard, I think. Yes. Because my presentation is in PDF. I hope it's visible. I announced here phonons in general, but actually I will be talking about acoustic phonons, which are the lowest in energy and which are well described by elasticity theory, very well known. The elastic field has displacements which can be quantized, and then we get phonons. Why it's relevant and why it's interesting to study the anomalies. Phonons, unlike, let's say, optical photon structures, due to a huge difference, 5 orders of magnitude in velocities, they are very compact. So they are used as membranes at the nanoscale. And here you see an example of a generic structure of such devices, which consists of a plate. Here we have the thickness, And here we have the plane, and the plate is defined as lateral distances as compared to the thickness, to the wavelength of the excitation. So when we have at micrometers thicknesses, we have phonons resonating at the gigahertz. And here you have a plot where such a microwave plate is resonating at gigahertz frequencies. And we have a grid here which represents the interdigital transducers which transform electric signals into mechanical vibrations. And such stuff is used presently in 5G technology because it's the right scale of energies, of frequencies. But in general, the acoustic phonons are present everywhere, so they are propagating through any media and so on. You have probably known what happens at the earthquakes. The respective waves are called Rayleigh waves, which are propagated at the surface, and due to a reflection from the surface, they have a mixed polarization. It is the reason why the seismic waves have such a destruction, because they oscillate not in single plane, but in an elliptical fashion, so that the buildings are being destroyed. So from high length scale to very low length scale, we have still acoustic phonons present. Here you see another example how they can be used as in the sensor applications, as the plate resonates at certain frequencies which depend on thickness and material parameters like sound wave propagation in the bulk medium and other stiffness parameters. Here you have a few representatives. The frequency of resonance is very sensitive to the changes in the material. And changes in the material, here you have a few examples as taken from the website of the Institute of Microelectronics in Bucharest. They are fabricating sensors of pressure, temperature, humidity, and gases by using such resonances, and even dual sensors which can detect both temperature and pressure. Here you have, for instance, dependence of the resonance frequency on pressure for the mentioned Rayleigh surface waves, and to the right you have a dependence on pressure of the other kind of waves, because in the plate, unlike the bulk material, we have a very sophisticated spectrum which consists of several branches, and these branches, lamp waves, they go deeper into the thickness of the plate, and they behave differently. Here you have some parameters of the sensitivity of these sensors, so they measure in megahertz shift of the frequency on a single bar change in pressure. Respectively, you have dependencies on temperature and so on. What is relevant, one of the relevant requirements for the sensors is their predictable monotonic or better quasi-linear dependence on the external parameters. Here you have an application in measuring the thickness of the corrosion layer in the metal plate. You see different thicknesses correspond to linear dependence. Why is this important? Because these sensors, they have to have one-to-one correspondence between the parameter, the temperature, which, for instance, at ambient temperature influences the thickness. For instance, if you have a metal, it can dilatate with temperature, and so on. So these parameters contain the information on the external factors, and fortunately for applications, this is indeed the case in most of the situations with such thin plates. In the simplest case, we have three independent parameters, which here you can define them differently. For instance, the thickness of the plate, shear sound velocity, longitudinal sound velocity in a bulk material, or the combination, which is the Poisson ratio, for instance, which depends on the ratio between the two bulk velocities. So apparently everything is okay, no anomalies. The reason why this principle works is rather simple to understand. That's why here I have explained that when you calculate the dependence on material parameters, let's take bulk material, you can calculate the propagation through the medium. You have several layers, calculate the traveling time, and you have such kind of monotonous dependence on various parameters. So you can define the sensitivities here, which, as I said, for instance, this is the shift in the velocity on temperature, which depends on, as I said, on the intrinsic parameters of the system. Now, what happens in the plate? As I said earlier, the wave propagates along the plate, and in the thickness it bounces back and forth, so that it creates a kind of standing wave. And due to that, you have a mixed polarization. Now you see how the complexity of this simple plate spectrum, which consists of many branches, most of which are gapped. Unlike the sound in the bulk material, which starts at zero frequency at a long wavelength, here you have a whole range of branches. This is the dispersion here, this is the frequency, this is the wave number, and the symmetry S and A corresponds to the symmetry of the plate. This is the simple, apparently simple equation. So up till now, everything is still normal, and I will come to the motivation why I started to look for anomalies here. It will appear later, but notice here there is a branch which is not monotonous. It's S1, for instance, here, symmetric branch, which has a kind of minimum. What does it mean? It means that you have a phase of the wave propagating in the plate positive, and on this, oops, sorry, now it started to react. While on this part of the branch, the long wavelength, you see that the group velocity is negative, and group velocity defines the direction of propagation of the energy flux. So you have a wave propagating in one direction and the energy in another. And at the minimum, the energy is trapped at this minimum. Kind of if you excite with the laser, for instance, or with the transducer, excite at such wavelength, it will remain there. This fact is used in many applications for the characterizing the material properties, but also it will appear later in the very recently this strange anomalous dispersion started to be used in metamaterial applications. And now this is a dispersion anomaly, as I mentioned, and in the title I announced the parametric anomaly. What does it mean? As I said before, parameters are not rather, they have featureless, the spectrum has apparently featureless dependence on parameters, and here I give you a few confirmation from exact analytical formulas. Indeed, this is, for instance, a full spectrum of the acoustic wave polarized in the plane. So it's rather simple. There is no coupling to the of the polarization. A single polarized, and it can be solved exactly. You see what I meant with the monotonicity of the spectrum. Here you see the view graphs. Still everything is okay. The only mention I will do here is that due to stability, acoustic or elastic stability of the system, we have a restriction, a relation between shear and longitudinal velocity, which is, I'm talking about classical things. Still, here's an example of another monotonic increasing dependence of the spectrum with the longitudinal velocity. Here it's a shear velocity. When you fix, for instance, longitudinal velocity, you can obtain analytical dependencies. And now let us see closer into this anomalous dispersion part, which is zero group velocity point is the minimum in the symmetric and antisymmetric spectra. Interestingly, it can also be analyzed and no anomaly in parameters again. So everything is monotonous. So where is the anomaly? And why it was not seen before? Here it is. I mentioned, actually that was initially the motivation. They are now studying and recently started to study these strange dispersion anomalies in relation to the metamaterial behavior. For instance, in particular, the phenomenon of negative reflection. And here you have measurements which demonstrate that if you put two plates side by side, not a stack, but side by side, and let the wave propagate from one plate to another, at the border something happens. The two waves, the two plates have their own eigenmodes, they interact, and at the border they couple, something happens. It's called wave conversion. And due to this wave conversion, you see here the view graphs demonstrating the parts of the relevant parts of the spectra in different materials. The yellow is aluminum, and the dark is molybdenum. It's a subtle tuning of the properties which shows that you can achieve, by changing the parameters, you can achieve the crossing of the spectra in such a way that on one side of this construction you have a positive group velocity and another negative. This is what Vesilago, Pendry, and so on studied in optical systems, and you have a negative reflection. So in optics it's a negative reflection, but here they try to obtain the same effect in acoustics. And for instance, here you see this kind of two plates connected. In molybdenum, you have a kind of focusing, superlensing of the wave which comes from aluminum into molybdenum on the interface, and it concentrates, focuses in a rather narrow region near to the interface. Okay, they have analyzed a lot of materials, and what I have noticed is there is such a strange subtle result here, that a material with faster material with higher stiffnesses, for instance, or higher bulk velocities, goes lower in frequencies or in velocities than the material with the higher bulk velocities. Here it is the case of chromium and I think molybdenum. So I have studied this particular paradox and found, by scaling the equations I've shown before, that it is indeed possible to demonstrate that such situation is indeed not an artifact, it's indeed a solution of the Rayleigh lamp equations with the right scaling. And here you see an example of a cross-section showing that here you have a shear velocity increasing, and here the frequency, and the single branch, which has a dispersion anomaly, which I showed earlier, has also a parametric anomaly, which is a non-monotonic dependence on the shear velocity. So in this view graph, it's a three-dimensional picture of this situation. You have a dispersion. Q is the wave number. Here is the scaled frequency. It is scaled differently, as I said, to single out the anomaly with the longitudinal velocity. And here, notice this cross-section corresponds to this graph. You see a non-monotonous dependence, which is associated here lower, a little bit at the lower wave numbers. You have this dip. It's the corresponds to dispersion anomalies. So they turn to be connected. They make part of a single anomalous behavior in this extended space. Okay, I will briefly mention, here's another demonstration of the same result, but at fixed wave number, so that you see again this non-monotonic behavior. What's the use of it? Well, I guess I started from telling about the sensing applications where you have dependence of frequency on the bulk parameters. For instance, bulk parameters depend on temperature. And in solids, the bulk temperature, most of them decreases with temperature, unlike the air, in the air. So you vary the temperature, you increase the temperature, you change this shear velocity, you can move along this plane. Yes? At higher temperature, we are on this side, for instance, and at lower temperature, or we are inverse. At higher temperature, it decreases, it's here. At lower temperature, it's here. So it's possible, as I said, to accumulate the elastic energy by heating up the system, getting into this dispersion minimum, zero group velocity, and then you cool it down, it stays there. Of course, it disperses. So it's a kind of harvesting of energy, for instance. I don't mention many other applications, and one of them here, using this parametric dependence, I show that unlike the combinations used in modeling the metamaterial, negative refraction behavior in plates, I stress that it's observed in simple plates, not in materials engineered with resonance superstructures or phononic crystals. It's just simple plates. You have such an interesting effect. But notice that it was observed between different S1 and S2 branches using. I changed the parameter, and this crossing point, it's at the interface, as I said. They have to cross the two branches. But the wave conversion is important. And why does it happen? It happens because of the two waves from different plates. They have to couple at the interface. And the coupling depends on both on their symmetry, so they have to have the same, more or less the same symmetry, which goes along every branch, but also the displacement pattern. If you use different branches, it's weaker. While using this result, we can use the same branch for different material, and I guess it could be achieved a better coupling at the interface. So I don't mention many other uses of these anomalies. I have put here some possible applications. Phononic spectrum, of course, is strongly affected by the dispersion and parametric anomalies. This can be used in transport and other applications of acoustic waves in plates. I think I am out of...
Thank you.
Thank you.
Question, please.
I have one. If the variation of temperature delta T tends to 0, it's slide 5. This means the efficiency tends to infinity. It's correct? Because you have 1 to delta T.
No. I can roll it back, but you measure the correlations, the susceptibility.
Okay.
So you have to see the shift. The idea of sensing is the shift of frequency depending on the parameter of temperature, pressure, and so on. So,
and you mentioned gigahertz, megahertz, kilohertz. Why it's so? Why you didn't use one
first
units of measurements?
No, gigahertz, megahertz you saw.
Yeah, but
the
for
graph.
example, it's 6,000 kilohertz.
Yeah.
Yes.
Yeah.
From 0 to 6 megahertz. Then where it's gigahertz, you put just in megahertz and use one unit of measurement.
I was very brief on this point. You can measure any frequency range depending on your parameters. For instance, thickness. What they measure in IMT, in Institute of Microtechnology, it's in gigahertz. Why? Because the sensitivity is increasing with frequency generally. So and frequency depends on thickness. So we have a compact structure which you can put in an environment wirelessly without battery and measure the temperature.
Okay.
And this is submicron structures. So they're very cheap.
Yes, and when you talk...
Sorry, frequency you change by changing the thickness.
It's clean.
Parameter.
When you told about metamaterials, you mean negative reflection or negative refraction?
Both
But
reflection.
what means negative reflection? I understand, but reflection?
I didn't mention deflection, but you are right. They are doing this also. It's a reflection from the border. So you have a single plate, such one, yes? Because size matters. So it reflects from the border, goes back. Yes, reflection is specular, yes, in principle. But they found that it can also be on the different angles. That's called even negative reflection. But I was talking about refraction. So it's a kind of flat lens, a flat acoustic lens. You put flat border,
Yeah, I understand.
and the wave goes.
And are there some other experimental works on this topic except for those of MIT?
This topic, metamaterials, it's not from MIT.
Metamaterial, I understand, those with acoustics.
Sensors
Yes, no,
application,
yes,
which
yes,
ones?
yes.
Of course, there are plenty of works. The idea
And they
is
correlate with your theoretical?
it's just published in this year, physics letters, this thing. But the anomaly, the paradox is that parametric anomaly, it's in this classical system was not observed before. So I found it, I explained why I came to, it's like looking for a needle in a stack of hay. So the anomaly is somehow difficult to find.
Yes, thank you. Any question more? Thank you again. And the next talk by Efim Arama and co-workers, photoluminescence and catoluminescence of layered zinc helium sulfide compounds, thermally processed in sulfur vapor and vacuum, will be given by Arama. Yes, no? Is there? Vom cărcat, nu? Aha. Then next. The next talk then by Lyudmila Gagara and co-workers, synthesis technology for cadmium selenide, cadmium telluride heterostructure and characterization of their photoelectronic properties will be given by Tamara Potlog.
Thank you for presentation. cadmium telluride photovoltaic is the most cost-effective technology because of the low manufacturing cost, long-term stability, and higher module efficiency. More than 30 gigawatt of cadmium telluride-based module installed worldwide. Multiple companies are in production. Modules are shipping at up to 18.6% efficiency, and lab cell efficiency is above 22%. But the maximum theoretical efficiency of the cadmium telluride solar cells corresponding to a band gap of 1.5 electron volt is about 30%. Because there is a constant need to improve efficiency of photovoltaic parameters of the devices, the main aim of our study was to propose a new design of the cadmium sulfide, cadmium telluride solar cells. Cell efficiency can be increased by reducing band gap of cadmium telluride. At the room temperature, band gap of cadmium telluride is 1.5 electron volt. In order to improve efficiency, we need to lower the band gap. Literature survey show that the insertion of selenium into cadmium telluride improves the conversion efficiency from 17% to 22%. Cadmium selenide has very similar properties as cadmium telluride, has a higher absorption coefficient, a direct band gap with value of 1.7 electron volt. And in the present study, we report the investigation of the cadmium selenide thin films. We report the development of roads to effectively incorporate cadmium selenide lower into cadmium telluride solar cells, and characterization of the device produced with cadmium selenide. E foarte mic și... Cadmium selenide and cadmium telluride thin films we are deposited by closed space sublimation technique. Closed space sublimation technique is an industrial method and is attractive because of high rate of deposition of cadmium telluride solar cells and modules. The gross rate deposition of the cadmium telluride, cadmium selenide thin films depend on several parameters, such as the distance between substrate and evaporator, temperature of source, temperature of substrate, the pressure, temperature, and composition of the gas from the vacuum chamber. Therefore, in our study, a source and the substrate separated by a 20 millimeters distance are introduced in a controlled vacuum atmosphere, and the source was maintained at the temperature higher than of the substrate. Cadmium selenide and cadmium telluride thin films we are produced in about 30 minutes without an additional gas transport agent in the single technological cycle without vacuum evacuation. morphological studies show that the cadmium selenide in films deposited at different substrate temperature are polycrystalline without any cracks or pinholes, and have a good adhesion to the substrate. X-ray analysis of cadmium selenides in films also confirms the polycrystalline nature with a hexagonal structure with preferred orientation 002 that does not depend on the substrate temperature, but only intensity of the preferred orientation depend on the substrate temperature. The structural parameter estimated from this diffractogram are presented in this table, and we can see that the full width at half maximum increase with increase in the substrate temperature, but at 300 decreases. The same situation is with grain size. Only intensity of the reflection changes with the substrate temperature. XPS photoelectron spectroscopy was used to estimate the composition of the one of the as deposited cadmium selenides in films. The SAVI XPS spectrum in the whole binding energy region contains cadmium, selenium, and oxygen. XPS spectra of cadmium region of the cadmium selenides in films at different substrate temperature does not change position of the maxima with the variation of the structure temperature. Cadmium telluride binding energy correspond to cadmium selenide bond, and the variation of the intensity with increasing of the substrate temperature only influence the concentration of the cadmium. Here presented the XPS spectra of selenium region of the cadmium selenides and films at different substrate temperature. The same situation as in the cadmium. The position of the maximum does not change with the substrate temperature. The electron binding energy maximum correspond to the cadmium selenide, and only the intensity is changing, and this means changing the concentration of the selenium. And the XPS spectra of oxygen region also depends on the variation of the substrate temperature. The position of the maximum does not change, but changes the intensity. The electron binding energy of cadmium from bond with oxygen, and on the surface is formed cadmium oxide, and this cadmium oxide from the surface of cadmium selenide depend on the substrate temperature. The less cadmium we have in the case when the cadmium selenide was deposited at 250, and the much cadmium is in was observed in the case when substrate temperature is 300 centigrade. Transmittance spectra depends on the substrate temperature. With increasing of the substrate temperature, the transmittance decreases from 15% to 5%. Cadmium selenide are transparent static with the infrared region of the spectrum. Using tau relation with builds this dependency from which we estimated band gap that changes very slightly with changing of the substrate temperature. It's changed only with 0.01 electron volt. This result from the research of the photophysical parameters cadmium selenide help us to manufacture cadmium selenide, cadmium telluride in film heterojunction. For the cadmium selenide was used a thickness of about 2-3 micrometer. For cadmium telluride thickness between 18-16 micrometer. The thickness was varied in function of the time deposition, and the optimal temperature was used for cadmium selenide. For substrate was used 250, and for evaporated 517. For cadmium telluride was used technological temperature which we used in the structure based solar cells based on cadmium sulfide, cadmium telluride thin film heterojunction solar cells. After the deposition of the cadmium selenide and cadmium telluride on tin oxide, the structure we are treated chemical in a saturated solution of cadmium chloride for half an hour. Then the structure was annealed in air at 450 for 30 minutes. As back ohmic contact with the used nickel deposited by thermal evaporation. Here I presented current voltage characteristic of cadmium selenide, cadmium telluride in film solar cells in function of the thickness of cadmium selenide. The photovoltaic parameters such as open circuit voltage, current density, fill factor, and efficiency are presented in this table, and we depicted that photovoltaic parameters depend on the thickness of cadmium selenide, because the thickness of cadmium telluride was kept constant. The best photovoltaic parameters we have obtained for heterojunction with thickness of 2 micrometer for cadmium selenide, and reach the value of 5.64%. It is all known from theories that open circuit voltage is related to short circuit current by this equation. The photocurrent is equal with short circuit current, and assuming that current density is smaller than short circuit current, we we obtain the formula that shows that open circuit voltage depend on the intensity of the illumination. From the dependence of logarithm current density of open circuit voltage was estimated ideality factor, and in the dark this factor changes from 4 to 10, while in the case of the illumination changes from 2 to 1.7. Because under illumination the parasitic resistance such as series and shunt decreasing, and we can propose that in operation of the solar cells, the current mechanism flow is generation recombination. A large set of cadmium selenide, cadmium telluride solar cells of different thicknesses of the cadmium telluride and cadmium tellurides in films were fabricated, and analyzing this type, we can resume that photovoltaic parameters depend on the technological condition of the both component of the heterojunction. And of the thickness. The best parameters changing thickness of cadmium selenide and of cadmium telluride was obtained for thickness of cadmium selenide about 3 micrometer. Also, we are investigated the effect of the illumination on the open circuit voltage and short circuit current. The short circuit current is directly proportional with the light intensity, while the open circuit voltage tend to saturation. Is a good agreement with theoretical data. The spectral dependencies of the photocurrent for cadmium selenide, cadmium telluride heterojunction solar cells with different thicknesses of cadmium selenide show that the short wavelength decay of the photocurrent is controlled by the thickness of component of the and the technological parameters such as substrate and source temperature of the component. This result allow us to conclude that during cell processing, the cadmium selenide diffuses into the cadmium telluride, converting it from photoinactive cadmium selenide Wurtzit phase to a photoactive cadmium selen tellur allow, with a band gap lower than of cadmium telluride, which increase the photocurrent that is higher than in the case when is used in heterojunction solar cell pure cadmium telluride. Conclusions are that technology of fabrication of cadmium telluride solar cells depends on the design of the device depends on the technological parameters and depends on the thickness of components of the heterostructure. Technological condition from this investigation allow us to obtain photovoltaic devices with efficiency which varied in function of thickness and different technological condition from 6.1 to 7.6%. Thank you for your attention.
Well, we understood, of course, that the parameters of the device depend on the technological condition, but they are not so high, 6-7%. How do you think, how they could be improved?
Could be improved, but we need to put buffer layer between frontal contact and window, cadmium selenide. And another buffer is need for ohmic metal contact and cadmium telluride. Because cadmium telluride has a high Ock function of electron, and not metals that have that high Ock function. Therefore, we need to find allow with high Ock function or deposit a buffer that will improve maybe with 5-10% the parameters.
Well, thank you. Any questions more?
At the interface, the same. We have a lot of losses because the concordance of lattice parameter is bigger.
Thank you. Any question more? No, thanks again.
The next talk will be given by our colleague Eduard Monaico, and the title will soon appear on the screen. Okay, Eduard? The floor is for yours.
Okay. Thank you, Professor French, for the introduction. So the slide is not here. Oh, okay. So the title of my speech is Zinco microtetrapods covered by gold nanodots as a platform for the preparation of complex micro-nanostructures. Okay, the presentation consists from motivation, the choice of the technological approach, synthesis of the Zinco tetrapods, and some experimental results and conclusion. So I will not try to convince you that zinc oxide is very important material. There are a lot of study in the last decade is made on this material. I just want to attract your attention that functionalization of zinc oxide will give new possibilities to for new application. For example, I will try to show you the functionalization with gold nanodots, and the main question is which technology can be applied, because chemical usually is used chemical deposition, but there is complicated to control the space between the nanodots, arrangement, and so on. And the problem is that via chemical deposition we need to use some chemical to activate the surface, and this can introduce some impurities in the materials. Another opportunity is electrochemistry. Yes, but in this case we need to have zinc oxide tetrapods with high conductivity or relatively high conductivity. I will speak about electrochemical deposition, and especially pulsed electrochemical deposition, because It's have several advantages because here we can control the pulse amplitude, duration of the pulse, and pause between the pulse. The duration between the pulse is very important because there is a refreshment of the electrolyte inside of the skeleton from zinc oxide. So first of all, I want to show you some our preliminary results that was already published. We proposed a mechanism for gold deposition and naming this mechanism hoping electrodeposition. In the SM images we can see that a very large porous surface is covered by a thin monolayer of gold nanodots. So each dot is arranged around other dots, and it can be explained in the following way. So when we apply the first pulses, electrochemical deposition starts at the interface with semiconductor and the electrolyte, and some gold dots is nucleated. Applying pulses, the dot increase in diameter up to some threshold diameter, and in our case is about 20 nanometers. This diameter is related to the formation of the Schottky barrier because the difference of the work function of the metal and semiconductor is very high, and gold with indium phosphide, zinc oxide will give Schottky. So in this case, another dot will form in the place near this dot because it's more convenable energetically. So in this way, the dot creation, so forming the dot, stopping, hoping to another place, will continue until the entire surface will be covered with one monolayer of gold nanodots, like here the schematic representation. And of course we can stop the process, and in this way we have the surface with one monolayer of gold nanodots. So another advantage of the electrochemical deposition, before I will start the experimental results, I want to show you that it was possible to show some, for example, in gallium nitride freestanding substrate grown by HVPE technology, some defects are created in the form of this give fine modulation of the electrical conductivity. Optically, the crystals are relatively okay, but electrically we can see that here in the scanning electron microscopy and backscattered electron detector, some concentric rings are observed, and after electrochemical deposition, the gold nanodots are arranged along the circle with higher conductivity. This can be observed also in the cross section, and electrochemical etching also is sensitive to the electrical conductivity, and here we can see the nanostructuring along some direction that it's predefined by the growth of HVP crystals. I will some information because Professor Adilung yesterday made a very interesting presentation about zinc oxide and the technology of obtaining. It was possible to see the zinc oxide in the form of snow. It's a lot of zinc oxide. So briefly, zinc oxide are obtained via flame transport synthesis, and of course the zinc oxide it's in form of powder. To make our process electrochemical deposition, we make some pellets by pressing with this mold, as shown in this, and compressing different amount of material, we can change the density of materials. Another important issue that we observed, and more details is presented in the poster number 6. I just not speak about optical properties, XRD properties of the materials. I will show you some results on contact angle measurements. And what we observed, that as ground zinc oxide tetrapods showed very high contact angle. So the materials have strong behavior, hydrophobic behavior. Here we can see that some tetrapods of zinc oxide, they are on the water. Yes. Here we can see the shape of the water drop on zinc oxide tetrapods, and it's characteristic for highly hydrophobic materials. We solved this problem via thermal treatment. After the thermal treatment, the contact angle was reset to 0, because it's even not was possible to measure. It was absorbed, water drop was absorbed by the zinc tetrapods, and we can see that the zinc tetrapods are in the water. So after this step, it's possible to apply the electrochemical etching, because with strong hydrophobic behavior, it will not possible. So after thermal treatment, we didn't see some morphological changes. Thermal treatment allows us to make some strong interconnection between the tetrapods, and after electrochemical deposition, we can see that near all tetrapods are covered by gold nanodots. But in this image, we can see that there are some tetrapods that some nucleation dots are formed. This can be explained by the fact that in the material, usually our colleague from Kiel said to us that it will be not possible because zinc oxide is not doped. Yeah? We just synthesize zinc oxide and use it as it. And is characterized by high resistivity. Electrochemical deposition demonstrated that some tetrapods, mainly fast all of them, exhibit very high and good conductivity, and this is possible to obtain even a monolayer of nanodots according to the previously shown mechanism Hoping electrodeposition. So here we have a lot of dots in just one monolayer with thickness about 20-22 nanometers. This mechanism also was applied for aerogallium nitride. It was recently published in press, the paper. Professor Tiginiano also made a very wonderful presentation about aerogallium nitride, aeromaterial. And we also deposit gold nanodots on aero tetrapod. So briefly, if here we can see the aerogallium nitride, inside was zinc oxide, and during the growth of gallium nitride was removed the zinc oxide, and we have hollow micro tetrapods. And it was possible also via electrochemical deposition to deposit these gold nanodots on these tetrapods. So in conclusion, I can mention some important idea that it was possible, because our colleagues say that no, it's will not work because due to the high resistivity of the zinc tetrapods. But the most important, that the density of nanodots can be changed by the pulse duration, pause between the pulses, and some recommendation that our colleagues must elaborate technological condition for control electrical conductivity during the synthesis of zinc oxide tetrapods. And of course, this zinc oxide tetrapods functionate with gold nanodots can be used further as platform for growth of nanowires and elaboration of some novel hybrid nanomaterials based on them. Okay. Thank you for your attention.
Yes, thank you for the nice presentation, and the section is open for questions. Any questions? Okay, please.
From what point of view have you choose gold to cover zinc or tetrapods and not as
the technology was also tested for platinum. Why noble metal? Because it's a strong photocatalyst in the another process.
Okay, other questions? Yeah?
I have one question. So, like, I was also seeing the popular data represented.
Vă rog, liniște, nu se aude.
So, like, as you can see, on the tip side there is a polar nature, and on the arm side there is hydrophobic. So, I mean to ask is whenever we are giving thermal treatment, or we can say sintering, so it actually transforming from hydrophobic to hydrophilic, or we are giving some mechanical treatment. So, how through mechanism we can explain this thing, like how we are deteriorating the hydrophobic nature of the particular morphology, or we can say the morphology remains intact, but its nature get, like we can say, transfer from the hydrophobic to hydrophilic part. How through mechanism you can explain this?
Yes, sure. The arms of this plane is hydrophobic. But our explanation that we can transform from super hydrophobic to hydrophilic can be explained by the issue that they think that during the synthesis, some polymers, because polyvinylbutyl is used in this experiment, remain on the surface of zinc oxide tetrapods. And after the thermal treatment, this polymer is destroyed. And after that, the whole structure exhibits very strong hydrophilic properties.
Okay, but like before sintering up to like very high temperature, about 1000 degrees Celsius, like sacrificial polymer we are talking about, it already, for example, we can say removed out from the tetrapodal morphology. You mean to say like it, with a very few amount, it remains there, which contributes to the hydrophobic nature, and after sintering it get deattached, then it gives rise to hydrophilic part. Is it you mean to say?
It's not
Okay,
clear for me, but
during
it's
the coffee break,
we can explain more.
you can discuss a little bit into details. Yeah? You just came together and you can discuss. Any other question? If it's not the case, thank you. Okay, yeah.
Can you use your technology and put this nanodot in the whole sample, or only in the surface?
This is in the whole sample, not only the surface. Yes. Yes, and all, because this is important. You can cover the surface just with sputtering, but the importance is to have in volume, so in the inside of the pellet.
And what is the
thickness was several millimeters, but up to 5 millimeters, 1 square centimeter, and the thickness is 5 millimeters.
Now, if you use electrochemistry, the electrolytes change the composition, and how it is connecting the whole.
Yeah, the microtetrapods have 50 micrometers arms, so it's a very high porosity. So the electrolyte is without problem just flow inside, and the refreshment of the electrolyte is realized by pause between the pulses. So we can apply, for example, 1 second between pulses, and electrolyte is refreshment inside of the sample.
Okay, let's thank the speaker again. Thank you.
Thank you.
And we finished the first part of our section. Thank you to the presenters. And we see each other in 30 minutes here. Let's go for coffee.
Hello.
Good afternoon. My name is Lung Won. Today I present work with title Illumination Dependent Photovoltaic Parameters of Cadmium Sulfide Zinc Telluride Solar Cells. A principle of the intermediate effect involved in introducing impurity doping within the materials when get at different energy levels. Intermediate when the solar cells have a theoretical predicted power conversion efficiency of 63.2%, but the theoretical value are comparable to the efficiency limit of optimized triple junction solar cells under similar emulation condition, with efficiency 63.8%. Various approaches have been proposed to realize independent solar cells, including impurity doping, quantum dots, and dilute semiconductor alloys. Impurity doping methods have faced challenge due to non-radiative recombination channels associated with the impurity. Quantum dots have shown promise in achieving the intermediate band concept, leading to sub-band gap response and increased efficiency. Additionally, dilute semiconductor alloys such as indium gallium arsenium nitride and zinc telluride doped with chrome have been suggested, offering to enable intermediate band position based on alloy composition. The literature study highlights the realization of intermediate solar cells based on zinc telluride chromium fabricated using PLD. These intermediate solar cells have a significant efficiency value of 5.9%, which is 19 times higher than of an undoped zinc telluride solar cells. This demonstrates the potential of zinc telluride doped with chromium as a promising material for intermediate solar cells with improved efficiency. We obtained different structure based on cadmium sulfide and zinc telluride thin films. When the frontal contact was deposited on a glass substrate using different transparent oxide. After depositing the cadmium sulfide by close space sublimation method with thickness of 200 nanometers, zinc telluride films were deposited on cadmium sulfide films by close space sublimation method. After deposit different buffer layer and different back contacts. We created two sets of samples. A first set we varied to substrate temperature between 320 degrees Celsius and 360 degrees Celsius of zinc telluride thin films. The best result of the open circuit voltage, which was 0.48 volt, was recorded at the substrate temperature of 340 degrees Celsius, while the best short circuit current density, which was 1.50, 10 to the power minus 4, was observed in the structure deposited at 360 degrees Celsius. In the second set, we varied the source temperature between 560 and 600 degrees Celsius, keeping the substrate temperature constant at 340 degrees Celsius. The best short circuit current density was recorded at source temperature equal 580 degrees Celsius, while the best open circuit voltage was obtained at 1600. From the present result, we can deduce that the best photovoltaic parameters were obtained at substrate temperature equal 340 degrees Celsius and source temperature 600. When we obtained the sample with different deposition time of the zinc telluride thin films, 6 minutes, 12 minutes, and 18 minutes. Cells obtained zinc chloride deposit time of 12 minutes and 18 minutes show the highest open circuit voltage of 0.76 volt at short circuit current density of 5 10 to the power minus 4. Increasing the deposition time of the zinc chloride in films up to 18 minus cause a slight decrease in the series resistance of the structure and at the same time increase the value of the parallel resistance and the field factor. With increasing the time of deposition, increasing respectively and the thickness of zinc chloride in films. Zinc chloride has a high work function of 5.7 electron volt, which affect the semiconductor metal junction. To improve this junction, it is necessary to find a metal with a work function greater that of zinc chloride in films. The primary purpose of back contact is to maximize the generation of electrical energy from the source light absorbed by the cells. With this consideration in mind, a series of cadmium sulfide zinc chloride solar cells were fabricated, each incorporating different metal for the back contacts of the zinc chloride in films, such as copper, palladium with silver, nickel, and silver. As one can see from this figure on the table, the back contacts significantly influence the efficiency of the solar cells. From the current voltage characteristic, it can be observed that the most suitable metal for the cadmium sulfide zinc chloride structure is silver, which is deposited by paste. The front contact of photovoltaic cells represent the part of the cells that come into contact with solar light and play an important role in collection and directing the generated electrical current. The front contact can consist of multiple thin films and functional coating, such as layer of conductive material and anti-reflective coating. With this consideration in mind, a set of samples was obtained using various transport conductive oxides, such as zinc oxide, ITO, tin oxide, and ITO with zinc oxide. From this figure, it can be observed that the most suitable transparent conductive oxide is zinc oxide, as it exhibits maximum efficiency. The buffer layer contributes to increasing the parameter of photovoltaic cells through several mechanisms. Continual efforts are made to develop buffer material and the technology to optimize the conversion of solar energy into electrical energy in the most efficient and reliable manner possible. In our study, we explored the use of antimony, tellurium, and pedot as buffer layer. From this figure, it can be inferred that pedot is the most suitable choice for the cadmium sulfide zinc chloride structure. Cells with a buffer layer are more efficient than choose without a buffer layer by over 100 times. We investigate the current voltage characteristic for the best fabricated solar cells under different level of illumination is described by this equation. In this slide, observe it presents a short current, a linear increasing in the short current circuit density with intensity of the illumination is linearly. The open circuit voltage increasing with increasing illumination, but it is less sensitive to light intensity than the short circuit current. The lower field factor value on the solar cells can only be improved by optimizing of the junction configuration. The cell resistance is almost in variant with illumination, but parallel resistance drop with illumination. The analysis of the spectral distribution of quantum efficiency in solar cells revealed the region where the carrier generation and separation process occur is confined by the band gap value of both cadmium sulfide and zinc chloride correspond components. The external quantum efficiency for the cadmium sulfide zinc chloride agent evaporated solar cells is relatively low, reaching around 0.2 at its peak, which is suitable at a wavelength of 550 nanometers. Meanwhile, the internal quantum efficiency slightly surpasses the external quantum efficiency. The inclusion of a buffer layer on the zinc chloride absorbed before the deposition of the silver contact through evaporation increases the internal quantum efficiency to nearly 0.5, while the external quantum efficiency remain at 0.2. In the case of the cadmium sulfide zinc chloride like cells with a PEDOT buffer layer and a ohmic contact deposited from silver paste, the internal quantum efficiency slightly exceeds 0.5, while the external quantum efficiency remains at 0.2. However, when the zinc chloride zinc films is doped with manganese, both internal and external quantum efficiency value decreases to 0.1. Across all solar cells design, the quantum efficiency both internal and external at larger wavelengths is constrained by the zinc chloride band gap. In this slide, present the conclusion. Thank you for your attention.
Good, thank you. Some question, please. Who has a question? I have one. Can you explain why your dependence of this one, of the Fisher from the wavelengths is so narrow? So the spectrum is very narrow. Here is even as a line. And there is some explanation why these spectra are different. Can try to do it in Romania. The explanation. Puteți să spuneți în limba română. De ce ele sunt diferite? De ce e îngust, acolo e mai larg? Deja dacă ați măsurat, trebuie să fie o explicație. Sau cel puțin o presupunere.
Aici sunt prezentate pentru structura zinc cu cadmium zinc telur argint. Aici este...
Uitați-vă, noi toți citim ce pe perete. Dar dumneavoastră, din punct de vedere fizic, ați putea spune de ce acolo e așa, dar dincolo e altfel.
Aici e dopat cu mangan.
Bine.
Și se schimbă...
Adică manganul asigură linia subțire care sau...
Da.
Thank you. Some question more? Mulțumesc.
Okay. If you don't have another question, now it's time for the second presentation here. Fine dispersion and intensification of heat transfer at boiling in electric field on modified surfaces? No?
Cernic is absent, yes?
Yeah.
Because Bologa is not here.
Okay. Then we can move to the third presentation, the water-soluble zinc phthalocyanine substitute with sulfur-containing groups. And the talk will be given by Jakob Gutson.
I am Victor Suman. Represent the work the water-soluble zinc phthalocyanine substituted with sulfur-containing groups. Photosynthesizer, this one the key factors of photodynamic therapy, as photosynthesizer should exhibit some characteristics. High light absorption in the infrared spectrum, have appropriate energy for the triplet state to provide sufficient energy at the transfer to ground state. Possess appropriate quantum height. Possess long line time at the triplet state. Have appropriate and high stability. Motivation, because here is constant need for improving the effectiveness and tolerability of the applied photosynthesizer e propus. Synthesis for zinc tallocyanine, sulfur derivatives soluble in different water mixture and solution. Absorbant investigation of synthesis tallocyanine. Photophysical characteristic of fluorescent high lifetime study. Method of investigation the UV spectra of the solution will be measured using UV spectrophotometer. The steady state fluorescence spectroscopy was performed using a spectrophotometer LS55. Time correlate strangling photon outing, pursued to determine the fluorescence lifetime. Text spectroscopy was used to provide information of the types of chemical composition and physical state of some. Important equipment for the design of tallocyanine for PT is soluble in aqua solution. Very interesting solubility in water for tallocyanine is conferred by incorporation of ionic and hydrophilic substituents. Octachlormethyl tallocyanine used for the starting substance was obtained following a chlormetallization reaction of tallocyanine and zinc. This reaction is originally describing the patent of which the chlormetallization process performed which is chlormethyl ether, and is obtained by the interaction of power 4 oryl thionyl chloride in the presence of aluminum chloride and trimethylamine, the triethylamine. Sorry. The FTX spectra here, so the product changed along the bond characteristic of the tallocyanine cycle. The characteristic bands correspond to the oscillation of carbon fluoride bonds 318 cm along, and the oscillation of the argon CH group at 1281 cm. The chloromethyl derivat reactives is with urea to refluxin ethanol. The HNMRM spectra, it is observed that the peak at 2.89 and 3.60 ppm. Due to CH protons present in the compound, but overlaps with residual water signals. The peaks are at 6.93 and 7 ppm has been assigned of the protons of the amino groups. Under the condition of the basic hydrolysis of the telluronium salt, the respective telluronium derivative results of the acidification of the reaction medium. Absorbance spectrum of octachloromethyl talagenol zinc, extra talagenato zinc trimethylen isofuronium chloride, and talagenato zinc metaniol and dimethyl sulfamide. Absorbance spectra of talagenato zinc, we observe two bands splitting into this compound into distinct peaks. In the region 350 800 nanometer is typical for the monomeric form of zinc talagenin or for insignificant regression of zinc talagenin molecules in solution. Observance of target are established from the light of 347 nanometer, where emission bands are elevated at 382, 694 and 764 nanometer. Daylight fluorescence quantum levels of the isofuronium substituted zinc talanin are significantly lower but less tiny for unsubstituted compounds. This is indicative of substitution of the electron donating NH2 groups carries some by commercial intersystem crossing from the excited state to triplet state. Besplenă triplet decay profile for talagenato zinc oxides, methylen fluoronium, fluoride in dimethyl sulfamide, left and vinyl chloride, middle on the water right. Summary photophysical properties of synthetic compound. The quantum metals for singlet oxygen generates were assumed to be E.55% for talagenato zinc trimethylen isofuronium chloride and vinyl chloride and solution, and 13% for water soluble talagenato zinc trimethylen isofuronium chloride. The conclusion. The report the report of talagenato zinc compound based on obtained by the chlorametrization reaction of zinc talagenin represent of isofuronium groups at the end of the real substitutes of the macrocycle improve of the and solubility on aqua media and of the overhand load improve the linkage to novel metal nanoparticles for further research. The emissions of photoluminescence band of water soluble talagenato zinc trimethylen isofuronium chloride around 650 nanometer at a different high times in time. That solution of isofuronium group not only decrease the transition energy of C0 to C1, but also increase the C1 to T1 intersystem crossing convection. The oxygen delta generation occurs when you transfer from the first excited stage to oxygen phi sigma to ground state of air and vice versa. The quantum miles for the singlet oxygen generation were measured to be 3.35% of talagenato zinc oxides methylen isofuronium chloride in NVP solution and 1% clorată solubile targeato microtais etilen isoleronium chloride. Thank you for
Questions?
I have a question.
Yes.
Show please the previous picture. Good. No, 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 no. Next one. Next one. The conclusions.
conclusion.
Here is written. The last sentences. This feature suggests that the good. Фталося are promising nonlinear optical materials. What kind of nonlinear optical effects can we obtain from these materials? And what is the parameter that shows that these optical materials, nonlinear optical properties are available?
Pot să vorbesc în română?
Da, sigur. Adică, de fapt, n-ar fi trebuit, dar dacă așa, vorbiți în română.
Talocenana de zinc este un material fotosensibil utilizat de noi pentru tratarea celulelor cancerogene. El absorbe foarte bine lumina în neliniar.
Ce înseamnă absorpții nelineare?
Adică are spectrul de absorpție, dacă mă întorc înapoi, are spectrul plin de absorpție în domeniul vizibil, cât și în spectrul...
Asta sunt proprietăți lineare. Nelineare asta atunci când depinde de intensitate. Nu, în cel mai simplu caz are saturație. Bun, dar...
Are, fiindcă sensibilitatea la zinc-taloceanină pe tot domeniul spectral este diferit. În domeniul spectral vizibil are o sensibilitate, în domeniul infraroșu.
Deci, atunci când formulați ceva care concluzie, totuși ar fi bine să fiți la curent. Ce anume optica...
Aici este o scăpare mică.
De acord. Sunt și alte întrebări, dar asta de acum nu e relevant. Bun, mulțumesc. Bun. Good. The next report will be presented by my colleagues from Institute of Microtechnology from Bucharest.
Okay.
Adrian Dinescu, please.
Thank you very much for the introduction. So this is my talk for today. My talk is focused on fabrication at the nanoscale. In IMT Bucharest, which is the institute I'm coming from, we fabricate a large variety of nanoelectronic devices. And to fabricate them, we need to pattern them. And in order to pattern them, our method is to use the scanning electron microscope. Well, this is the outline of my presentation. After the introduction, I will continue to present a little bit the electron beam lithography with converted scanning electron microscope. Then I'll present the fabrication process for a field effect transistor on graphene, and finally I'll conclude. So this is my experience in using 3 scanning electron microscopes. This is one with tungsten heated filament, another one with field emission gun, and this is machine, a scanning electron microscope converted for electron beam lithography. I will explain later how. Everybody knows the scanning electron microscope. It's a common tool in any research laboratory. Inside the microscope, an electron beam is generated, and when the beam interacts with the substrate, here a lot of signals are generated. Backscattered electron, secondary electron, so we have a compositional image, topographical image here, and also X-ray are emitted. And when X-ray are emitted, we can perform energy dispersive microanalysis, so you can identify a lot of elements, chemical elements in the substrate. Of course, we can measure the critical dimension in scanning electron microscopy. This is important for microelectronics and also for fabrication. But the main purpose of my talk today is to explain how the scanning electron microscope is used for patterning. In semiconductor industry, or in any research laboratory dealing with fabrication, it doesn't matter how simple or how complicated is this device you need to fabricate. There are four main processes involved. The first is thin film deposition, we have patterning, lithography, we have thin film etching, and of course we have implantation in order to create on the substrate to fabricate PN junctions. But the mostly used is this patterning, lithography, because after each process you need to perform patterning of your structure in order to draw the device. So, in order to pattern, a few words about the lithography. Lithography is a very easy process. You need to cover the substrate, working on it. For example, a silicon wafer, cover it with electron resist or with photoresist. Then the photoresist is exposed, or electron resist. And after that, after developing, we got on the substrate, the pattern. This is lithography. We can continue the process by etching, in order to transfer the pattern on the substrate by etching. This can be done by etching, or by depositing a metal layer, and after the liftoff, we can get some electrical contacts on the substrate. Well, for lithography, we can use, as you can use in IMT Bucharest, photolithography. Everybody uses optical lithography. That's very simple. You need a mask, a photolithographic mask, a mask aligner, and after using it, the whole wafer is exposed, and you get the pattern. The problem with optical lithography everywhere is the resolution. The resolution is only about 1 micrometer because of the diffraction of the light. Wavelength of the light is there, 1 micrometer, half of a micrometer, it doesn't matter. Anywhere the resolution is half of about 1 micrometer. Of course, we could use these tools, the steppers. This is amazing, yeah. The resolution of these tools is very high, below 50 nanometers, below 20 nanometers. But for this one, which is the most expensive, the price is 500 million euros, only for this one. Okay, so this is for production, for industry, it's not for us. What is for us is the scanning electron microscope, yeah. If you have the scanning electron microscope, then we can add this part here, which is some electronics in order to transform the microscope. That's very easy to transform the microscope for lithography, which means the raster scan generator of the microscope is replaced by the pattern generator. So the beam doesn't move anymore in a raster, but it will move according to the geometry we put on our computer. Okay. Just a few words about the electron beam. For any electron microscopist or for any engineer working in patterning, in lithography, this is the most important part of the beam, which is called electron probe, yeah, which is characterized by the beam diameter, beam current, beam convergence angle, and accelerating voltage. The art of lithography is to, to get the best parameter, because every time they are contradictory. The smaller beam diameter, the higher the resolution. But the smaller the current, and you cannot see in the image what you are doing there. In fact, the patterning process is very simple. If you have the tool, the wafer is divided in a lot of chips. Every chip is divided in write fields, and every write field is written like that. Why it is not written in a single step? Because the electron beam cannot cover, in a scanning electron microscope, cannot cover more than 100 by 100 micrometers. So in order to cover everything in large field, you have to stitch some things. And then it's a little bit complicated. You have to calculate the dwell time, which is the time the beam spent in a single position. Yeah, it's in the order of microseconds. But I have to emphasize one thing. Electron beam lithography is a very time-consuming technique. The beam stays in the point just a few microseconds. But the beam diameter is very small, it's something like 2 nanometer diameter, and you calculate, if you try to cover 1 square micrometer in nanometers, you have more than 1 million dots. Yeah, something like that. Okay. So, the third part of my talk is focused on this. Many times my colleagues, they ask me to fabricate field effect transistor on 2D materials. So, this is a typical field effect transistor with source, drain, and the channel here. The channel, the blue part is the graphene in this case, and this is a cross section. Anytime that the substrate is a silicon wafer covered with silicon oxide, because you need an insulating material otherwise directly on silicon is short circuit. So this is the graphene, the blue part. We have the source, the drain, okay, and an insulating layer and the gate. The gate is able to control the current flowing from the source to the drain. But the thing is to fabricate this as a micro scale, at a nanoscale. very small. With optical lithography, it's very straightforward. But what if they ask you to fabricate, for example, the width of this channel to be 100 nanometer? That's why we need the scanning electron microscope to fabricate it. So the typical process is like that. We need to fabricate some alignment marks or register marks. Why? Because we need to overlay everything. Fabricate the channel, then we need to put precisely the contacts for the source and the drain. And then the gate, and every time we need to be precise to put one layer on top of the other, very, very precise. Okay, so something like 5 processes, and I would like to describe each of them very briefly. So at the beginning we have the alignment marks. This is patterning in PMMA. PMMA, polymethyl methacrylate, is a typical electrolysis. After patterning, the sample is covered with gold, chromium gold by evaporation, and after the liftoff we have these alignment marks in gold, 80 micrometer in between them, and this is very precise. Yeah, okay. And the next step is to shape the graphene, to get the channel, the graphene channel, yeah? A very small graphene channel. You cannot see here because this is an optical image, but I'll show the next image, a scanning electron microscope image of the graphene. The smallest part here should be very small, like here, yeah? This is 2 micrometer, the width of this one is something like 500 nanometers. So this is the graphene channel. We should put the source here, the drain here, very precisely, and then the insulating layer, and then the gate. So, another patterning, yeah, the sample was covered again with PMMA, and we patterned the source and the drain on top of this. And after applying the metallic layer and after the liftoff, okay, have the source, the drain, and in the middle is the channel. Okay, you cannot see the channel now, but I'll show you later. And after that, the insulating layer was deposited, which is the insulating layer in this case is a negative electron resist, HSQ, which is in microelectronics, it is, the name in microelectronics is liquid silicon dioxide. Okay, it's very useful for this kind of lithography. And then we have to pattern on top of that the gates. So we have the source, the drain, and this a little bit yellowish part is the HSQ, and this is the pattern in PMMA again for the gate. There are 2 small gates here, I'll show you later. So the final metallization is that one. Okay. So this is the final device with everything, the source, the drain, and 2 gates, because they wanted, my colleague, they wanted to perform some, to fabricate some kind of logic gates, logic things like that. And if I'll show you on this silicon chip, I fabricated 25 by 25 devices, okay? And each device is like that, like I showed. And if you look in scanning electron microscope at one device, this is the middle, yeah, the center of the device, like here. And here you can see the source, the drain, this is the channel, here are 2 gates. And if you look at the gates, this is a HSQ layer, and if you measure, the width of this one is 100 nanometer of the gate, yeah? No, in this case it's 42 nanometers. And the distance between the gates is something like maybe 500 nanometers. So 2 gates controlling the current flow from the source to the drain. Okay, this was one device. We published a lot. They asked me to fabricate the gate tilted, because tilting the gate on the graphene, we can control in a different way the current flow. And after that, they asked me to produce more than 1, 2. 2 is much more difficult because of the overlay in this small distance. And then more than 2, 5, and even 10 gates on top. Patterning 10 gates is kind of fabricating a very small grating from metal. And for other devices, they asked me something different. For example, again for graphene FETs, this is another channel, but the channel of the graphene was patterned in this manner. I fabricated in the channel here a lot of holes. Yeah, the distance between 2 holes is 100 nanometer, and diameter is something like 25 nanometers. So no illusion, cannot get this with optical lithography. And also for other devices, this, for example, this is a diffractive optical element. It's a very thin, a Fresnel lens. Okay, this is silicon patterned by electron beam lithography and then etched by deep reactive ion etching. And in the final, we have a very flat lens. It's like a lens, but it is very flat, a Fresnel lens. Okay, and in the end, I like to show you, we published a lot of for negative differential resistance in graphene ballistic field effect transistor with oblique top gate. Okay, a lot of papers with these devices, and not only on graphene, on any 2D material, on cadmium sulfide. The last device I fabricate now is on thallium selenide, and also we have a very tough project on fabricated this kind of field effect transistor on very thin silicon layer on SY, silicon on insulator, fully depleted silicon on insulator. And these are the conclusion of my talk. I think I'm in time. I like to say the scanning electron microscope is a very versatile tool for both for imaging and for fabrication. Application, I told you about the applications. They include field effect transistor, FinFETs on SY, surface acoustic wave devices. In the previous session, one of the colleagues mentioned the devices fabricated in IMT Bucharest. So I fabricated the surface acoustic wave devices operating at very high frequencies on piezoelectric materials. Okay. It looks simple at the beginning, but if you try to fabricate it, it's not like that. So thank you very much.
Thank you very much. Question, please. I have one. Did you try to do this on the two-dimensional materials like transition metal dechalcogenide, like molybdenum sulfide or tungsten sulfide?
Molybdenum disulfide. I did it.
Yes.
The key is not patterning on that. The problem is to know how to etch them, because I can pattern with a mask, and then you need, in order to define the channel for the field effect transistor, you need to etch.
Because it can be more interesting than to use the graphene.
I'm very open for any cooperation if you provide me the material on
Yes,
a flat
of course.
substrate.
We are able to do this.
If you do this, then I can fabricate devices, field effect
Okay.
transistor on this.
We will discuss about it.
Thank you.
Încă întrebări? Would like to ask something? Bun, so thank you very much. And the last report, our colleague Leonid Konopko from the Institute of Nanotechnologies and Electrical Engineering, Electronic Engineering, of the Technical University of Moldova.
Good afternoon. I will talk about quantum installation in topological insulator bismuth silveride selen microbias conducted with superconducting Indi-2 bismuth layers. Mistake here. This is the outline my talk, introduction, you can see. Bismuth 2 tellur 2 selenum is a topological insulator. A topological insulator is a material with time reversal symmetry and topologically protected surface state. The surface state of topological insulators are special since they are topologically protected by a time reversal symmetry and no non-magnetic disorders can destroy them. Here in topological insulator we have Dirac Coulomb with a surface state which is a linear dependence of momentum, and in topological this is a schematic of this material, and angle resolve emission spectroscopy show clear that this is a linear dependencies of energy to momentum. What is interesting in topological insulator? Topological insulator have a surface which behavior of surface is like a very good metal, is very high conductivity. But in the bulk, this is a insulator. We produce small microwire, glass-coated microwire from this material, and using for this process Litovsky-Taylor method. You can see in this picture the brief shortly technology of this process. This is scanning electron image of cross-section of microwire. The diameter equal near the 20 micrometer. We measure the thermoelectricity of this material, power factor, and in magnetic field came some changes in these values, but our material have not very good, but very normal values of thermoelectricity, minus 150 micrometer per Coulomb. And for micro cooling purpose, we use single crystal made from this material, and we using exfoliation method produce the single crystal thin layers. And these layers possesses very good parameter because of this very thin, and maybe in these layers exist quantum size effect. Topological superconductor ED2 bismuth. Very interesting. This is a superconductor which have three critical field: first, two, and third. Because and the third critical field is a surface superconducting field. And the last paper on this material was published only in 2021, and the author of this paper is very known Andrew Game. This is maybe the first topological superconductor which was investigated in all methods. We produce this material and measure, have measured, and the temperature determines resistivity shown here, and we have critical temperature 5.7 Kelvin, and here we measure critical magnetic field, and critical magnetic field was near the 0.2 Tesla. It's very clear to this data obtained in this paper. When we connect interface of topological insulator with superconductor, we can obtain very interesting phenomenon. The interface is of particular interest because it can give rise to novel phenomena such as creation and manipulation of Majorana fermions. These quantum particles are their own antiparticles and exhibit non-abelian statistics, making them potential building blocks for quantum computing. Here I show the schematic of this sample. We use two materials for contacting on the left hand. On the left side we use gallium. Gallium have superconducting temperature near 1 Kelvin, and in our measurements from 1.5 Kelvin to 4 Kelvin, this material is in normal state, and here is indium bismuth, TC 5.7 Kelvin. No, here bismuth 2, TOR 2. And this material, this sample is shown here. What is the, this is some mathematics. If we have two frequencies, the difference is very small from one to another, we have summary oscillation with beating. And here we can calculate the one frequency and another frequency from two parameters, from the beating period and from the oscillation period. We use this knowledge for our analysis of our experimental data. In our experimental data, we hear magnetic resistant oscillation in our sample, but the start of oscillation starts from the magnetic field 0.1 Tesla. This is a magnetic field of HC2. At this magnetic field, our indium bismuth solder in normal state, and in this case only surface superconductivity take part in this oscillation. We can see pronounced oscillation and beating pattern. Using this parameter and after fast Fourier transform, we obtain two frequencies. These two frequencies, and using the magnetic flux quantization in the multi-connected closed surface, like the ring, we can, and using the magnetic flux H divided 2E, this is superconducting magnetic flux, we obtain from this analysis two parameters, D1 and D2, like in this picture. And this is the superconducting region of interface topological insulator and topological superconductivity of indium bismuth. And from this data we can obtain this DR, the width of this cycle, width of this ring. On this width equal 16 nanometer. No, this is I show the ring, but the picture is more complicated. This is not ring. Here the transverse magnetic resistance. Okay, we can see in our sample in transverse direction quantum oscillation which we connect with quantization of magnetic flux. But if we see look at this sample, we cannot see some close ring. No, this is a small.
Why?
Huh? No. But we can see. This means that inside of this exists somewhat very interesting. We measure the longitudinal magnetic resistance of the same sample, and in this case we obtain some not so good, but the same oscillation, but they're different two frequencies, and these frequencies connected with this type of ring. The D1, D2, they differ, but the width of this ring the same, 15 nanometer. What we have? I must speak that the very difficult to get contact from India to Vismut and Vismut telluride, very difficult. And maybe this contact is very, very small, and this contact have very complicated picture. But if we show this likely ring, we see that this in this point we have a ring with in some ring, and in this case, in transverse magnetic field we have this area. In longitudinal magnetic field, this area, and okay, and we can explain our result. And what is interesting that in this phenomena участвует only the surface superconductivity of India to Vismut. This is very, very exciting. Okay, conclusion. They produced, we obtained, and what is very interesting, that the effective width of close superconducting area of the topological insulated superconductor interface is determined to be 15 nanometers from analysis of the spectrum from transfer center. And I must say that penetration depth in that paper, they obtained 65 nanometer, but we have in this interface only 15. That's all.
Thank you. Question, please. Who has a question? Tell me, please, Leonid. Your sample is in glass, I understand.
Yes, in glass.
Because there is no interaction between the glass and your sample, your nanowire.
No.
Between the some influence.
What is the different? No.
This one is the glass.
Yeah, okay. This is glass. This is our sample. Maybe not so much. Not. We have no engagement.
I understand.
Yeah.
Because at low temperature, I guess that this interface has to be influenced by.
Yeah. No, okay, but the interface, this is inside of this area, not in the glass, but in the.
Yeah, I see, in the wire.
The wire.
course, thank you. More questions? Thank you. Yes, please.
Have you tried to change the concentration of one of this element from your allowance?
То есть change the
The composition.
concentration,
Composition,
composition.
да. And try to measure
we cannot try to change.
resistance.
We have sample and we measure it. Because of this sample was obtained in maybe 10 years ago for thermoelectricity. This is the best material for thermoelectricity.
It was before the nanophysics.
Что дали, то и сделали. Что вы прям
Good. Thank you very much once again. Finished. Our session is closed.